So hello, welcome everyone. Hopefully you can hear me. I'm joining here today from Dubai. We'll be visiting with my company GitX conference. So let's check. So can you hear me well? Plus minus. If there's any problem, you can leave a like, or maybe when you like something, leave a like. So but yeah, you hear me. Okay, great. So there'll be another exciting small piece towards the ability to implement deep learning papers. So basically, at the end of this course, you will be able to take a paper and implement it without any kind of GitHub or other implementations. And today's piece will be the object-oriented part of it, and we initially started looking at it, and now we're coming back to that. We will join all of the things that we learned before about linear algebra calculus, and we'll start actually implementing proper deep learning techniques like how to embed and encode different data types. So it's the dummy solution is just feed in, model anything you have, and then you have not really good results. Even though nowadays, as I in the beginning of the course said, AI is widely used to structure unstructured data. Even the unstructured data should have some kind of format, not just randomly dropped into the model. So yeah. And let's, if any questions, then just write in the chat. So my plan is now to first look at the previous lectures homework, and I saw lots of submissions, which is a good sign. Then we can learn together and see what works, what not. This is very important in order to succeed this course. And also need to remind you that those of you who succeed well in this course, there's a lot of opportunities in research, in the academic, commercial, so on. You can work on your thesis with me, but the prerequisite is that you're basically good at this course. So if you don't know these things, then it's very difficult to work with somebody who don't know these things. Yeah, but so let me share a little bit the last task, and then we'll look at what's possible. We cannot copy it for some reason. Just again. Okay, now I copied it right. So there was a task to implement second version of the model that we tried in the class. Also, the last time when I was in the person, when I was able to come in person, there was a situation that students who were in person requested that I do not make it more complicated than it was. So I did not add the multidimensionality as an input, but I saw that some of you did add the multidimensionality as input, which is good, which we can discuss and look together, and then do this today properly. So what we have here, so first, only Numpy is allowed, so please, hopefully you did not use SciPy and all other hacks. So we need to learn how this works before we start implementing fancy hacks, one-liners, and so on. So then use the mean square error. I think we already used that. Okay, maybe not. So yeah, right, we used mean absolute error. So screenshots, I saw lots of screenshots, that is good sign. If you don't submit screenshot, I assume that doesn't work. So then so then the inputs could be the year and the mileage, right? And there's some like normalization applied to that, and the outputs could be the price, I think. Right, so the input model could look something. So not the input model, but the shape of the weight. So what it means is, so it will project from 2 dimensions. In this case, 2 dimensions are what we have 2 dimensions because all of these details very important to understand. So release of year, right, and mileage. So these are two dimensions here, right? And the output dimensions are the hidden vector, right? So this guy, maybe just to remind you visually how it looks like, I gave you also this playground tool to play last time. That tool could be used to kind of better visualize and understand what's happening inside these models. But mathematically, the ideas are really, really simple. So for example, if I drop in this seam that I had last time, and I'm not sure did this time or last time for sure, we will start working with the with the softmax as well and classification. For meanwhile, you can ignore the softmax part, but the idea is that here would you have two input dimensions, right? And there would be 8 hidden dimensions here, and this could be any dimensions you want. Like normally, if you have like high resolution image, you would have, let's say, and so the normal pipeline looks something like this. You have so let's say the images some 1 to 4 times 1 to 4 times 3 colors, so about 3 million inputs. In reality, we would use some not as dense model. Even the vision transformers do not have the full context for the images. So then the next one would be, I don't know, we could drop it down to 1K hidden. We would actually call all of these things features. If you see anywhere name features, that means that dimensionality. So features, and here's also the input features. How I got the 3 million input features, let me explain. So I'm talking about if this would be an image. So I got it by 2024 by 3 channels RGB. So that's how you can get such a large input feature. This would be then 1K, and then you would go down. Let's say here would be 0.5K, 500 basically input features. Usually they are powers of 2, because so let me see, 256, yeah, 252. So because the powers of 2 works fastest on the GPUs. So and then here at the end there would be some output. In this case, if we have price, there will be 1 feature. Also, one important thing, maybe those of you who try to do this, you have the batch or the sample count, all of the samples, like 4 cars, right? And then the output dimension, which also must be as a 2-dimensional like that. So it's not, you cannot just have comma B, the output. It will not work with the matrix multiplications. And in the beginning, this is 3 million, right? And in the middle, it is B comma 1K, right? And then there is a B. So I'm just showing the shape of the data points that are going through the model. You will get it more and more clearer. And just like if you start to think about this is important. So what I'm trying to illustrate here is that normally this is like a neural encoder. You start with the high dimensional and you go down to the 1 price dimension. Like you have the input of the car picture and the output is the price, 1 number. Like if this is like Ferrari, then it will be 1 number. If this is like Suzuki, there will be another number, right? So, and how we achieved that, just for you to remember, we used the matrix multiplications dot products. And maybe this is also a good point starting to talk about this, and we will talk about that a lot today. So is that if I want to go from 3 million to 1K, so how do I do this? I project down, like I tried to show you in the camera when I was in classroom, like a shadow, right? 3-dimensional object shadow on 2-dimensional plane. We do the same thing here, and the first weight 1 would look something along lines 3 million, 1K, like that. So this is the matrix that would be applied to get from, we're gonna change the color. This is nice to have a different color. Where is the color? Let's see. Right, let's like that maybe. Yeah, so and how the mathematical operation is really simple, right? So in the brackets, I'm showing the shapes, the sizes of the matrices, not the actual contents of the matrices. This is exactly the same way how it works in Python. So, and here's the mathmul operation, or the dot product, which is two-dimensional operation, right? So if I apply that one to the x input, which is the x input is here, so let me here, yeah, so this is the x, and then I get the h, which is this guy, h. Hopefully you followed this long. If there's any questions or not something clear, please write stuff in the chat and I will explain more about that, so everything is clear. So once already you can start seeing some funny things here, and that was something that I tried to explain at the end of the last lecture. So the two-dimensional algorithm, right? So this is bad and this is bad because this is two-dimensional and we definitely don't want to learn anything from B. So the B is the number of examples in our dataset or batch. So like, for example, we have 4 cars, then I don't want to learn the features that are related between 2 cars, like what is common between Suzuki and Ferrari if they are located in the dataset points 1 and 2. Like, this is a stupid question, right? And this is exactly what would happen if I would do the dot product like that, because it would try to find what are the correlations between the positions in the batch, which is like whatever, like if the Ferrari is the first position or the fourth position, I don't care about that. I care about the contents of Ferrari. So because this is two-dimensional algorithm, that's why this happens. You remember in very beginning I deleted something. Oh, okay, cool. So in very beginning we talked that and we implemented as a for loop, as 2 for loops, basically the two-dimensional algorithm dot product. Now how to resolve this? There is an easy trick how to resolve this, and this is very important to understand. So because otherwise everything goes very sideways. So you basically expand dimensions. What I mean by expand dimensions, you would do something like b 3 million, 3 million, 1, which does not change the data. This is also the students sometimes do not get. If I add here 1 in any place, I can add here hundreds of one-dimensional spaces, and I will just add these square brackets in. You would imagine like some kind of JSON or Python lists, right, or arrays. I would just add bracket, 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 bracket. That means 1. It doesn't mean anything else. So, and after this operation, now it looks really good. So why it looks very good? Because let me explain. I will look at the chat in a moment after my speech here, right? So if I do this guy with this one, right, it will get out. So it will be repeated b times. This will just mean repeat, because it's a two-dimensional algorithm. It works on the last 2 dimensions, and Numpy is so good to us that like similarly, like if I add some number to vector, it will repeat that operation to every single element. So that, and the result then becomes something that is also very favorable. So we will get result of like that. And then if I squeeze dimension, if I just remove the extra square bracket, I kind of feel that I need to show you about the square brackets again, because maybe it's not intuitive for everyone at the beginning. Now I get a nice hidden state, right? So this operation is basically what I tried to show last time, where I add this non or new axis or expand dimensions and then squeeze or select the zeroth element. So this is basically that, and then we will do that today as well. And I saw something like that in the works. So yeah, just before jumping in the homeworks, and I'm started to talk all about this because here is the optional task. This is optional. I don't force you to do that. The main task for the homework was actually to implement this model, And the 10H part, either you could derive it yourself, which is not super crazy hard, or you could find the derivation on internet, basically, if it's true, if it's correct, maybe in Wolfram Alpha. And all other Lego components are given here, right? So they are just really like a components, because we have linear layer that's already implemented. This is a new stuff, linear, and then we just multiply, and we need a new loss function, which is, I think we already implemented that one with gradient in the robot arm. So basically everything is quite easy here. The difficult part is these dimensionalities. So let me explain a little more about dimensionalities before looking in the homeworks. So something that sometimes students do not get immediately, but this is very useful in general for any kind of programming. So let me show one example. So here, if I have an array or some, let's say, input features X, right? So, and if I have, well, let's use the same example with cars. So if I have, let's see, so if I have here the prices of cars, so there will be one car costing 20K, right? I know that I can write it with E, but just for the visualization. So one other car is 15K, then another car is 5K, and so on, right? So we have 3 cars here. The shape, x dot shape, looks like 3 comma nothing, right? This is definitely not good shape for any kind of deep learning, because we want to eliminate the samples themselves and focus only on features. Again, why I'm saying eliminate samples, because samples because the dot product, which is the main vehicle, main mathematical operation, or I would rather say two-dimensional algorithm, that is driving the deep learning models, that is two-dimensional. So it's not working on one dimension. That's one. And then I want to repeat this algorithm for every sample rather than mixing them together in some kind of strange patterns. So how then I can do these things is something along these lines. So if I add in here just another bracket around, I don't change any data. That is the very important thing, because sometimes students do not get it, that if I'm adding the additional dimension, it does not change the data, it just changes the shape. So now it looks like that, and it's still not good, because I could not do two-dimensional with that. If I do two-dimensional with this, then I will do a strange combinations of learning why in my data set they have this order of highly priced cars in the beginning. So next time when I put in the model some data, it would say, like, if your samples are the first ones are most expensive and the last ones are the cheapest. Basically, that will be the learning, which we definitely don't want. So because we want to focus on each car's unique features. So here, if I add another dimension, it would look something along lines like this. So 2 brackets, again, data don't change. I have 1 here. I can also do some strange things like these, which are not needed for deep learning, because I could do, like, at least here it's not needed. I could add brackets around here, and then it would be 1,3. Okay. And I can do combinations of those as well. Of course, I can do something as crazy as this, like just adding here brackets around this. But basically, the kind of, I will just highlight which are the most important combinations to remember how to work with them. Is like 99% of the cases you would have something along this one and this one. So you need to know how to go from there to there, or maybe also there. So I know I would say rather there and there, right? So these are the typical combinations. Oh, I made a color here. When we talk about image data, it's a little bit more complicated, but the same idea. There's no difference there. Okay, so this is my rant so far. Let's double check with the audience. Hopefully I shared at least the right screen, otherwise I would talk myself. So yeah, I'm looking. Okay, so there's not lots of pluses. There's 4 likes. Okay, so let me ask a question before jumping into the code. So are the dimension things clear? Like if not, which part should be explained more? Okay, so I'm writing in the chat. So if it's clear, then type plus. If not clear, write what's not clear or minus. And again, why I'm talking about this is 2-dimensional inputs. You see there is this weight matrix, which is not anymore just one number. It is matrix, not number. The inputs also needs to be changed in higher dimensions and then remove the dimension so that the dot product algorithm works on the last 2 dimensions. Okay, so let's see. No answers so far. At least if you all say minus, then probably we'll keep going and explain a little bit later again. But maybe some of you got it, or at least so far. No response. Do you hear me? Okay, there is at least 1 plus already coming in. Okay, that's good. That's good. While you are checking in with the chat or maybe writing some question which I can answer, we will start share the code and we will start exploring what people have been doing in home, and then we will jump into today's session, which will be hopefully quite exciting because basically we will start working with some methods that are directly applicable to many real-world tasks. The only difference is that the real-world tasks are done with the PyTorch, and PyTorch we will start exploring next week, basically. So okay, so I'm sharing the code. So there were a couple of submissions, and this submission seems to be the idea of having 2-dimensional stuff here. Kind of looks really nice in the first place. Except like I'm not. Oh, this is weird. Maybe so. Sometimes I don't even know that Numpy updates functions and do things that I previously was not possible. But normally this is not possible. Normally you would use either the operator at, or you would use the matmul, because dot product actually is something else. So let's see. So normally you would use matmul like that, not dot, because as soon as you start working with this 3rd dimension here, okay, you have 2 dimensions. Okay, I think so this might be that the reason I just explained that maybe if it was used by dot, that it learned the location. So what it learned if this sample is located here or here, rather than is this important or maybe that important. So yeah, normally you would use matmul or at symbol, not dot. So this is one thing to learn maybe here. Okay, let's go step by step deeper into this. Maybe I will share the full screen so I can make notes better. Okay. So here for sure, like always, np matmul or at, right? Not dot, because dot would not work correctly with higher dimensions. Only if it might be that Numpy changed something, then maybe it works with higher dimensions. We'll see. Okay, so I will change it actually. It works backward compatible as well. So this is correct. It might be taken from might be taken from somewhere, but this is, so I don't see actually the derivative for the loss, which is extremely strange. Where is the derivative for the loss? dl. All right, it's here. Okay, but yeah, it'd be nice if you would use the same notation like DMSC loss rather than just hard coding it somewhere down. Be better to follow the code. By the way, the PyTorch also is very much like this, like where you have small modules and you combine them together. That's nice. Okay, so I probably will need to have a debugger here to double check what's happening there, because dot product could not be there. Okay, the loss plot seems about nice. Okay, let's see. So the D loss sum, okay, the right, this is interesting. Where it went down, okay, DL, okay, this is W, right, okay, I see it. Okay, we'll see, we'll try to understand what's happening here. Okay, so DL pred, something is missing here. It really don't see the derivation of the linear layer itself. I see the dot product with, okay, the X, right. So this is that's why it is super complicated. It will get so complicated that you yourself will not understand the code at all if you will write it like this. So this is a spaghetti script, which is completely not debuggable and understandable, because if I would write it like this, it makes much more sense. Or I could also like even write it even more clear, which should be, this is like some kind of D of some linear layer, right? So this is D of W of linear 3 or something, right? So something along those lines makes so much more sense. Also the middle parts, right? Now, if this fails, the only way is then you will need to have, you cannot even have a breakpoint here. You will need to change the code just to debug it. So this is really not a good way how to write code in any project anywhere. Like is it like like programming or mathematics or so on? This is very bad way to write code. But okay, so there is that thing, and then we have linear. So I just want to debug and understand. I believe that this summation stuff maybe affected things in a way that it should not affect, I believe. Let's see. Okay, let's see the breakpoint. Because I'm really confused about using the dot instead of matmul. So okay, let's see. So this is the first one. This is the shape. Shape. So ooh, this is also bad. Right. Okay, this because it's, I guess it's a weight of 4 by 4. How this could happen? So so we have 4 sample. Why this is not good is because, okay, here's the 4. So because with numbers that are the same, it's easy to make bugs. So I highly recommend to use different numbers for batches and for, so I know this is like not power of 2, but for debugging purposes. So highly recommend use different numbers. So I also here some, okay, B, right, this is cool. So because otherwise if there is a mathematical problem and you have the batch the same size as the feature, very easy to make mistakes, very easy. And also like, of course, if you want, you can write neurons, but really they are not neurons. That's very far away from anything related neurons. But anyway, so this is I know it's called artificial neural networks, even though nothing related to artificial neural networks, the same way as genetic algorithms, nothing related to genetic algorithms. So but still very powerful methods. very powerful methods. If somebody wants to research something that is closer to actual neural networks, you need to study spiking neural networks, and this is like artificial spiking neural networks, but this is closer and also not close enough, so basically far away from the real brain networks. So because they work completely different way. So okay, so shape, that's why I never say neurons, because they're not neurons. So shape 5.4, okay, so that's good. That's good. And here this one, shape 4x1, okay, I guess also okay. So we'll see what happens after here. So this should be the shape for the matrix derivation or Jacobian. So 5.1, and we can easily check if everything is right. So there's many ways how to do something wrong, but at least we can check like that. So this is 5x1, seems about right. Seems about right. And then this summation, right? Something is not right. Why it works? So there's a 4 by, okay, the matrix itself, it's 5x1. Okay, it worked because that dimension was the same. So, and this is 5x4, but something is off here. Something is off here. Again, let's try again, because of the first one I don't see anymore. Okay, so this I have DL. Okay, let's check one by one. I don't want to stay forever here as well, but so this is all good. So 4 samples by 1 feature, 4 samples by 1 feature. Then here this thing, 5 samples by 4, because there is the transpose at the end. Okay, so it is transposed. Okay, 4 samples by 5 features. 4 samples by 5 features. Something fishy going on. That's good. Then H, X. What about X? If you even don't use here the linear function, it's so complicated, so hard to follow, because there's not used the proper modules. So shape 2x8, right? Yeah, so I think what's might happening here is something that's called Numpy broadcasting. So it kind of understands what you want to do and probably adds no, but it actually is possible to do the matrix multiplication with this one. Right. Okay, so it works here, but this is definitely not safe way how to do this. So we'll try again later, but like it's like mathematically seems really nice code here. It's just like the way how it's written, it's not that nice. And also, please, for the future, don't use dot, use matmul, and use extra dimensions, because here it seems that, at least from the first look, it seems that it actually did the 2 dimensions, these two with these two. So it took in account the positions of the features rather than repeating them 4 times. So that's what's happening there. Okay, so let's go next one. Next one is not what it's needed. So, okay, there's MSC. So this is okay. That's the loss, right? Okay. There's just combination of the existing code, but model doesn't look right. Okay, where's the model? Yeah, this is not what I asked to do. Okay, this is not that good. And what about loss? Oh, so this is not, yeah, this is definitely not right. So if person, oh, This is very, very wrong. So if person who did this tried to do this with a hand, right, to have the derivation with derivation rules, then probably the person made mistake here. But if it's like, if the person was like very convinced that this is a correct way, this is so basically it's not so the derivation is wrong here. And if you have the wrong derivation, the funny thing is that sometimes things actually work with wrong derivations, but they fail silently, basically. So this is not good. I forgot to add here the spaghetti code. But please don't write spaghetti code, especially in mathematics. It's so bad. As I told you before, I had some mathematicians who were like debugging the code for weeks, which they wrote in a couple of hours, because they did not use normal, like line by line explainable code. So layer. Okay, this is also not cool. Do not make the outputs on return. Again, not debuggable. Like, you want everything to be super debuggable. You will see yourself later that if you cannot debug your models, it's like really nightmare. So something like that. Okay, the loss function again would be nice to pull it out from here. Also, I don't get fully why do you do that. So this is kind of some kind of strange normalization method. Also, you see there is no minus in front. This could be true if the y prime is in the other order. But I think in this case it shouldn't be the other guy. So here's, oh no, it is the correct order. Oh right, and there is also so for some reason you want to, okay, you want to use the scalar there as for the mean value, I guess. Okay, if you want, leave it there. Normally you use it later. So okay, this looks good. Except again, very similar as the previous person, do not use these functions that you already made yourself. So the next one, okay, extreme spaghetti code. I hope that I last time did not do it myself like that, and it seems that person also do not understand how to build models at all. But okay. Oh, and I also don't understand how to write Python code. Okay. Yeah, so you definitely need to learn on the Python coding. Definitely need to learn on like just follow along the what we will do again today. And any questions, yeah, improve. Like just so this is quite far away where we need to be here. So next one. Okay, this is okay. I asked not to. Whoa. That's interesting. Okay, so there's some kind of function modeling stuff happening, and okay, so there's first thing that I can help in any models, like I would say 99% of the time on any models you would never use random for bias. So there's always bias is always initialized by 0. Also in any modern models and so on, it's never random. In some models even don't use bias, by the way. So that's that. There's something interesting going on here. Okay, and again, spaghetti. Be nice to see anyone not writing spaghetti. So, okay, this is good. I like it. Even the person added for reproducibility. I forgot to add this last time. Oh, I see also that there is something going on nice with the shapes. So this is really nice. So what it means is I'm seeding that every time that I run this code, I will have the same random numbers. So they are like random, but they are just from the same seed. Yeah, this is very useful. We use that all the time in machine learning, because machine learning is often based on very random stuff for the initialization. If I want to compare, this is not bad at all. Also the shapes, I know this works, I think, but normally people write like that, I believe. Oh no, this is right, this is not size. Okay. Do Python have size? Yeah, but Python have size, right? No, it doesn't work like that. Okay, the PyTorch have size. Okay, cool. Okay, so this looks interesting. So okay, now anyway, so yeah. So normally, like in again, I would say never actually nobody writes biases like that. So for biases, there's 100% of the time you delete this part and you add that extra one, right, dimension in the training procedure, not in the weight. So it's basically you always look at your data from the last dimensions perspective, not adding some helpful stuff here. So that's something to remember. It's almost like in any models, never they do something like that. But it's great to see that a lot of people tried this to solve these problems themselves rather than just generate some code that they don't have any understanding what they're doing. That's really nice to see, because it's kind of easy to see if it's generated. It's like they had like too smooth and like not like human. So but anyway. Yeah, so I see that in this time this is like a nice way that there is the more values, and this is also fun. This is really fun. Yeah. Okay. So this is not really correct implementation, but you could implement it with the idea that you basically iterate through your every sample in the batch. And then in that case, yes, in that case you could use dot product. So then the dot product would work nicely. But what is wrong here is that, so don't want to go into crazy details, but basically the idea is that you could do this like second for loop, and actually in reality, when you don't have enough GPU memory for huge images, you do something similar like that. But what is wrong is this part. So you would never definitely try to update after every sample. You would do this after the whole batch. So after the whole batch would be somewhere here, basically. Right. So wait, is it the batches? No, the batches is here. So yeah, so this would be epoch in our cases is just the whole batch. We will have mini batches as well, maybe even today. So, and the idea here is that this guy is actually what you are adding. So you would do something like that in reality. So I know it's like the person who wrote this probably understands what I mean here, but basically it accumulates the gradient and then executes the SGD once after every batch. So this is one way how to do this, but I like that there is some creativity here. And also I see these reshapes with -1, so there is the idea which I described before. Okay, the next one. We cannot go through everyone, probably. Write some questions in the chat, we'll check on that. So again, the same stuff here. Normally don't ever do that. There's no training loop here. There's just one iteration. Yeah, what is R1? Okay, here. Okay, yeah, so you use the optimization here a little bit, just to reuse the variable. Yeah, it's very strange that you don't have loop here. So the next one. Yeah, you see there's these yellow stuff. It means that you mix tabs and spaces. In Python, you use usually just tabs, most cases. Again, the spaghetti. And again, it seems that not really that complete understanding of what we are doing here, but at least the tanh derivative, where is the tanh derivative? It's not here. So yeah, so this is not good understanding of what we are doing here. So we've had at least 2 students already who do not follow at this moment, but yeah, we'll just maybe keep pushing, and maybe you will get there, but you need to work a lot on yourself. Otherwise it will not succeed. Okay, so you used my method here. Yes. By the way, after the lecture, I remember that visually better method is this node. So we will do that probably today. Basically, not use new axis, but instead use the keyword none. Then it works. It will work then in PyTorch, in any framework. It just looks more cleaner like that. But yeah, so that method is important. Yeah, we'll see how it's implemented. I think let's go. This will be the last one. Then we jump into days. Otherwise, we will not have time because I have also some good stuff happening. So this is this linear. Oh wait, here's the. So this is definitely not right. Oh, there's 1 1 0. Right. So this is something went really wrong here. So this part is nice. This part is definitely not nice. So there should be for sure the dot products or multiple operations, and these should be matrices. If they are not matrices, then all of this part doesn't make sense at all. So yeah, the next one, gradients. So this is back propagation. There is also, you see, B2 gray. It means that it's not used. Something is wrong here. Also, the idea of returning tuples. So this actually means that you return huge tuple here. This is also not optimal because you might mix up something here and then it would fail. So that's just some advice. Okay, so been following this for a while. Let's go back to something more useful for today. We'll see in the chat if you have some comments. Okay, no major comments. Okay, no more likes as well. So okay, let's then look at something interesting. Okay, now I will probably open the new template. Before the new template. So the Kaggle. If any of you don't know, the Kaggle is the place where people, scientists and companies share the data sets and give the competitions to scientists and students and so on. And then they compete, and sometimes they even give prizes for these tasks. And the idea is that you need to solve them using different methods, and there is scoreboards and so on. And this is the data set of the used cars. I think it's in India, the Indian rupees. I think I already converted it to euro in the data set which I will give you. And we will try to implement this stuff in using Numpy and object-oriented programming. So this will be a little bit different way how we did this last time. It will be much more clearer, hopefully, like much more like Lego-like. And just to see what is yeah, let's go step by step. So first I will open, then the task. The main idea is that that we will use much more features, like, so it will not and samples. So there will be like thousands of samples and many features, like we could use even dozens of features. I think there's 8,000 samples and many features. So that's the plan. So this will be 5.2 model. I'm now opening it in the Moodle. So edit mode. Assignment 5.2. We'll explain, show template, and we'll go step by step building our, I would say this would be like our first proper model. Like this would actually work on some real case scenarios, like some simple scenarios, but still. Yeah, so I think I shared 5.2, please get it. Meanwhile, I can share also what we need to build. Yep, so 5.2 sharing on the whiteboard. And we'll go with you that from the code. Here's also cool stuff. So when you register in Kaggle and look for datasets, there you also can see here the histograms. So these are called histograms, like bins. So you divide the region limits from 1992 to 2020, the cars, and how many are in each bin, right? And you definitely need to clear your dataset. So this seems quite clean dataset actually. I think you can have more columns somewhere, I don't know where. And you see also the petrol, diesel, like almost 50-50, and then there's some, like I think LPG is very little. So there is imbalance here. So what you really don't want, and this is very, very important, and I have seen this in commercial companies, in academic research, everywhere, that you can have really bad and like unpredictable and counter-predictable results if you have unbalanced data set with anomalies. So there you see, like, basically it's quite clean, but if you would see some spike like far away from distribution center, this means you need to clean your data set. Probably here is something not right, because selling price from 20,000 till 8.9 million, probably this area should be cleaned up. So this is that. Yeah, I opened the task. Please get the template. Hopefully you got the template. If you didn't get the template, I will also post it in the chat here if somebody joining from outside, and then later in the notes maybe as well. Okay, cool. So this will be, I cannot post long stuff. Okay, let's just post template. Okay, template I can post. Great. Okay, let's go into the code and explore it together, and we'll explain about those features and all sorts of other things. I think there will be a couple of significant updates today, which needs to be understood. And if you understand them, they will work very well in the future for many, many tasks that you want to do with deep learning. So, okay, let's jump in here. We'll make it larger, maybe. You know, my lectures is the best to work if you have, like, either in the live classroom, and you can see on the whiteboard the video, right? Or you have two monitors, maybe. Otherwise, I believe, of course, it's not optimal. So, but it's important to write yourself code, debug, think about it. Otherwise, like, link together equation with the code and so on. So here we have learning rate. This is the alpha step. We have a new stuff called batch size, and I already started to introduce it. So the idea here is that I will split my 8,000 data samples by 16 size mini batches, and then use those to train models step by step. And this is actually along those lines, which I already showed, that there is one person who submitted work where you update gradient one sample at a time. If you do that, it actually, yeah, maybe I have some image. This is significant. If I will have an image, I will share it to you. I thought I have one. Oh, I have it, yes. Didn't want to cut it. Copy image. So why use mini batches, and why not update gradient just one by one sample? Of course, one answer is why I don't want to update my gradient by one sample is because I have GPU with parallelization options, right? I can, like, compute thousands of samples in just one sample in the for loop, which is really not great idea. But then why not use either all right samples, or so basically if I update one sample, one is from the optimization procedure, but other thing is that, so the red one will be one. So I randomly start here, and then I start going here, and then suddenly I get maybe some other sample, and I immediately go here, and then I go back here, and then I go, so all over the places. Of course, the jumps are about the same distance, but I'm jumping all around the place, and I never land in the optimum location in the loss function. So if I'm doing the same thing with the whole data set, so in some cases I even cannot read the whole data set in memory. In this case I can. Probably all of your computers probably are powerful enough to do this, but we will not do this, because what happens? So if I would now use the whole data set, not each sample separately, to update my gradient, let's see which color I can use, maybe orange. So I would start, for example, here, and then after every update I would be basically about the same place, and I would never move outside there, because the gradient will be so small, so the direction will be like always going not to the deepest part. So because all of the samples, only in the case if the data set is uniform, normally distributed and perfectly aligned with some kind of correlation, then it would go very fast down. But otherwise it will not go fast down. It will just stay around in this small region and never go anywhere. So that's actually reality. So one by one sample jumps around everywhere, learns nothing. All data set also learns nothing. So what else we have? We have mini batches. Mini batches, it works in two ways. One is it optimizes the procedure, so I can load not whole data set but some part of it, and also it generally goes in the right direction basically. So, and then you have a question how big mini batch to choose to not go in there or there, but this is the way how models in any models are trained. There is also very often situations that you cannot load in your GPU memory more than one image. Then you virtually convert this situation into that situation. So how you do that is you accumulate gradient the same way as I showed you before. I just not do the update after every sample, but plus it, and so on, and then do the update once in let's say 3 or 4 samples and so on. Yep, I hope that's clear. That's very powerful actually. So okay, just jump back here. So we are loading the class dataset, and this is car deco from my server, and then we need to normalize data. Maybe we can use this time some other normalization method, and we also have the X, which is the input features, Y is the output features, and labels are the labels for the classes, for the categorical features. Then we have data loader. Data loader is this thing which I just talked about. It is converting every symbol get item. So if any of you have never seen this, you can play around with this like this, and encourage you to do that. So do we have actually dataset full? Yeah, we have it down here. So we have a dataset full here, and if I ask dataset full, so let's say print dataset full 0 and exit just after, so we don't crash code, it will execute. So this dataset 0 will execute the get item function. So this is basically dataset some index, yeah. And this one is len operator. So anytime in Python you see 2 underlines at the end. In the front it means private, at the end it means operator. So in here it's dataset len. So that's what we're getting there, okay? And the data loader changed that. So data loader makes that it collects from indexes samples, random indexes samples, and creates these mini batches. And here what we have, it's even more interesting maybe, because what we have here is, so iter operator is executed when I call for something in dataset loader. So not for, but when I enter there, so basically it's this each So, and this is executed when starting, and the last one is executed on every step, You see how valuable it is if you can make an object that is operating like a collection with a for loop, right? So this is that. We'll get to that in a second, and hopefully you will like it. So then you create these two options. So the train dataset and test dataset, and you split it by this one. So, and there is, where was it? Hopefully it's defined. It should be defined somewhere. Yeah. So 70% for training and 30% for testing, and there should be somewhere. I believe there should have been somewhere the random seed, but I don't see it. So then the next part is the variable. So the variable part is this very interesting object, which is exactly the same in PyTorch. If any of you have ever started working with PyTorch, you might not know, but every single tensor is like this, and parameter as well, so that you have the value, which is the forward pass, and grad is the backward pass value, and these two are like stored together in a single object called variable. And then this single object variable, oh, there's a bug here, please fix it. I will also note in my notes that I have a bug there. There was for some reason to these two equal signs. Bug here, need just colon. I'm not sure if in your template you also have bug here, but you need to fix that. So I will update it. So let me get through the code, and then we'll start coding. So the linear layer, we already know this, but we'll have forward pass, backward pass, and in PyTorch this is exactly the way it works. You always have forward pass, always have backward pass for every single mathematical operation. In this case, this is the linear layer operation. So there's the sigmoid as well, ReLU, squared error, absolute error, model. Model then becomes really fun, because model is really like a Lego. There's nothing else there anymore. Optimizer is the same way as we did with this SGD here. The only kind of interesting thing to note here is that you can pass parameters, and parameters are actually, maybe I should type it properly. So list of variables. I will maybe put in my notes that I need to type my code better. When I did this template, I did not pay much attention of typing, but typing actually helps to understand what we are doing here. So we are like fishing out all of the variables from the model, and then training only those. But the gradient is flowing through the whole model, also the parts which do not have variables. So what I mean do not have variables? So remember, for example, the sigmoid do not have variables. Well, it takes variable, it produces the variable, but it do not have variables to learn. But linear layer have several of them, like W and B. So that's that. Then we have the loss function here at 2 to 8 line. And then we have the loop. So this is very typical loop of the training. So you have epoch, which means going through every single sample in the train and test dataset. So then there is the train and test datasets pointers. So these are not anything magical here. They're just two pointers to objects, and these are passed here. And then we are going through every single batch. So X and Y is not samples. They are batches by 16 samples at once. So that's that. If something is not clear so far, please write in the chat, and we'll start coding this slowly together. Yeah, and then there is the loss plot at the end, the nice picture. So we're collecting the losses, average losses in each batch, and we're adding to the train and test losses. There is a very important stuff about that. We will talk about that as well. Okay, let's start working with data up there. So we could implement some other normalization method maybe. Let's see if I have equation at hand. If not, yeah, I have. Great. So I showed you last time the standardization normalization, if I believe, like with sigma, right? There is other way how to do this. There's many ways how to do this. No one right way, but there's definitely a lot of wrong ways. So easy to detect also the wrong ways. So okay, so this is this. So the normalized means that, like, if I want to have normalized between 1 and 1, minus 1 and 1, then I use this formula, for example. Let's do that. So how to do this is, then you always want to store your original values, so x min and y min. Please write the code with me. If you're not catching up, just know me in the chat, right? And last time to time, if you're catching up, you can catch up also a little bit later. If you definitely know you will not be able to catch up, so but follow along. So min, so this means a minimal value. If I would just leave it like that, it would be just simple number, but you will see in a second that x contains, remember, as in the last time, the production year, the mileage, the number of gears, number of owners, all sorts of crazy things. So that's why I'm using axis 0, and this means which axis I want to eliminate, which axes are not important to me. In this case, the original shape was, let's say, 8,000 something, comma, I believe 4. Let's double check if I had some notes about that. You will, in the debugging, we will see. Oh no, it's actually six features. And then after applying this, I will get just 6 feature minimal values. If I'm not applying axis at all, it will got 1 value, the absolute minimal value. If I use 1, then I will get 8,000 sample, 8,000 output, which will be the minimal value for each car, which I don't want. So this is correct. And I'm storing these min and max because these are useful, because then later I can use them in production, because in production I cannot just create a new min max. And also I can use that in inference for prediction, like if I want to return from normalized value into real value. So, and how to normalize then. So let's try to do this with the equation that I gave you. So so use the same x. So self x means, so the self x minus, let me see, should I calculate deltas? No, I can't calculate deltas. So self x min divided by self x max minus self x min. So this is from 0 to 1, or right, and I made a mistake here a little bit. So in top part there should be another bracket, another bracket, and like that. So this starts to look a little bit spaghetti, but not too bad. So self x max, so this is a plus divided by 2. I'm just using the same equation that I gave you. So that's that. And in the bottom also divided by 2, like that. So it should be from minus 1 to 1. You could actually use the same function, not to repeat it twice, to define it. So because y also need to be you need to be normalized the same way. So how they normalize the y? Either I would make a function or copy code, which is, copy code is not good idea, but to write a function, it might be too complicated right now. So anyway, I could write a function. It's not too difficult as well, but the space on the screen is limited. So y, don't leave x's somewhere. So y, and then I will debug it, and you will see what's happening here. So y. All right, so this is a price and something else. Oh, there will not be 6, there will be 2 features. So another really cool thing is here, we will predict not only price, but 2 features at once. And in deep learning, you can have any input features, any output features. You can project down to 1 feature, or you can project up to many features, which is also cool. You can have generative models that generates high-dimensional, high-quality images from very little input of the text, for example. So I had here breakpoint. If you have any questions so far, please ask in the chat. So debug. Okay, cool. Self-X. So what we have in self-X, lots of stuff here. So what would be the best way to explain what we have there? Actually have some notes. Okay, we'll see. So this is what we have there, and if you look, did I add it to the, yeah, I added to the whiteboard. So if somebody didn't follow this code, it's added here. If I have a mistake, please let me know. So slide 10. So then in slide 11, I'm posting this, which is the dataset structure. So we see that the X values, so first is brand index, then it's fuel index, because these are the labeled stuff. So it means that there will be Audi, BMW, so on, the fuel, diesel, gasoline, transmission, automatic or manual. All of these are indexes. What I mean indexes, it means that it's 0, 1, 2, 3, 4, and so on. It's not a scalar value. And it actually means that we probably should not try to normalize it. But let's do step by step. We definitely don't need to normalize them, but let's do step by step. So then the seller type, that's also, so these are all categorical values. So we should not normalize categorical values. So these should not be taken. So this, you never ever feed model this. So this is completely wrong, but we will get to that. But it will learn something, but it will definitely not be good. So and then the year of make, right? This is a scalar value. So it could actually be also a categorical value, but in this case, this is scalar. So you have 199, I don't know, like 2020, 2000 something. Actually, when I'm thinking about that, the ability to go from quantized categorical values and just these scalar values which are continuous. This is interesting topic, because I believe sometimes it's not the case that you need to have scalar values. So and then kilometers driven. This is again the large numbers, right? So and the output values is how many owners has been and what is the selling price, and we will predict both of them at once, not separately but at once using the matrix operations. Okay, good. If something not clear so far, let me know in the chat. So we can see here. So these last numbers. So this is the year made and the price. And the first ones are the, for example, what means 0. We can decode one of these guys. Okay, so let's decode one of those. So this is my target, which I want to decode. So I would use labels 0 and 2. So this is Honda, and then 1 and 1, petrol car, then 2 and 0, manual car, and then 3 and 0, individual seller. I hope you get it, how I got this. I will show you in the whiteboard as well. So there are these four first features which are categorical, and that those are different than the last two, and also different than the predicted ones. And if I want to do the classification task, those would be very important. But at this moment, we are still doing a regression task, which is prediction of the scalar values. So here, how I did this, if somebody didn't notice. So this is the value 2, right? And it is here. And the same as value 1 is here, and so on, right? So these are the values which I queried in the labels, because these are categorical values. And the indexes here on the other side, these are also important, of course. These are just the order of the inputs, right? Like this is the 0, 1. So this is the 0, 1, 2, 3, 4, 5, like that. Hope you get it. So this is how we decode the data. You will always have data in these formats. Like it's never like ChatGPT type of data where you can write it in unstructured way. You can use unstructured data and then use AI to structure it, but it will not be 99% accuracy. If you want super high precision models, it will need to be that way. So. And this yeah, so that's that. So we have this thing. Oh, I didn't check if it's from 1 to 0, minus 1 to 1. Let me check. So x, yeah, it seems about right. Okay, we can double check using this thing. NP max, it should be 1. Oh, maybe something is off. And but I saw there is a minus 1. Oh, maybe yeah, should be higher. So minus 25, right? There's some mathematical stuff happening. Very strange. So x. Okay, it's already all right. I cannot go back even now because it is already converted. But let's check some things. Okay, it should have been minus 1 to 1. Now it's 0.25. That is funny. So solve x. Let's see, NP min. Or I already have it here. NP min is this thing. So 0, 0, okay, 0 is not a good number at all. This is scary number. Okay, but there is a, if there would be 0, 0, then this would be bad here. It would divide by 0, and then everything would blow up, which is definitely not cool. So then I'm just thinking this could happen several reasons. So let's see this thing. So divided by 2. This scalar, this is some very small number. Something I don't like about that one. Go and check the formula. If you see any mistake, you can help me as well. Why max when minimum? Okay, it doesn't care what order. So that the bottom part, like we could decompose it in a other way as well. Okay, I will just write it in my way, and then I will find where is my bug. So if I would do 0 to 1, so 0 to 1 looks like this, divided by this. It should be 0 to 1. Hopefully it is. We'll check. Yep, so this is 0 to 1. Great. So then if I'm now minus 1, so I need to minus 1 something, so minus 1 of this thing. we'll look in chat, maybe you found already some bug. So -1 this thing and times 2, all of that thing, then it should be -1, -1 to 1, at least in theory. Ooh, -2. Okay, I did again something stupid. Okay, 0, right. Oh, I know, 0.5, sorry. Like that. Okay, now it should work. Max. Great. Now this works, and the other one doesn't work. Need to look where is the bug. So divided by. Okay, let me see in the chat if you see something. If not, we'll just use my formula. Okay, you're not finding anything. Okay, let's use my formula. It should. I guess it's actually funny that I think it's the same formula. Yeah, something is off here, but maybe because the brackets. Okay, let's the last attempt. We'll try to do the brackets correctly. So now I have all the brackets in all the places. We'll see if that helps. Where's the bugger? Yep, it helps. Funny. So basically, the both formulas are correct, but the original, which I started to use, needs another bracket around here. Otherwise, it probably what it does. So it will divide by 2 everything that's happening, like after all of this stuff, I guess. Yeah, so need to have a bracket here. Okay, great. So this is the normalization procedure. Again, you would not normalize the categorical features, just normalize these. Great, let's keep going. So this is something I put on the Jamboard. Okay, I will update slide number 10 because that's what I have there. There is a bug there. Okay, cool. Slide number 10 updated. Okay. And here we have the selection of the row of the x's, row of the y's, right? So then we go to this interesting stuff for the dataset loader. Actually, if I run it, it should work, at least I hope. Yep, here I get the data points. So yeah, so here we need to implement the next phase, which is the data loader. And data loader is also kind of really fun to implement. It is design pattern. It is the design pattern of iterator design pattern. So it means that usually this kind of design pattern is used when you have database connections or like infinitive scroll, for example, where you don't know what is the end of the. You can just load every sample on the fly. So self index batch, this means we will count our batches till we get to the end, and each batch will contain of something. So if the first thing is we will, okay, yeah, if index of batch is longer than self, which is actually this thing. So len self is that thing. Maybe I can just write it. That, and this is the number of batches. Not samples. And this double division means divide without the so divide it as an integer, basically, with the floor. So here, raise stop iteration. So this means I want to stop the iterator pattern. So then index, let's say index start. We have index start and index end. This will be self index batch, index batch times batch size plus self index start. So from where we start, we do the same thing. Oh, we can do it different way. So for the end, so index start, I think it'd be easier just like self batch size. There is a trick there. Sometimes the last batch is not the same size, which is kind of also not very optimal, but that's what we have. So then x and y equals self dataset, and now the cool stuff, we can just query our previous class like that with that operator. This is very powerful stuff that we could do here. And then yeah, we need to index the index batch, so we increase the batch number and return x and y. And x and y now will not be just one car sample. It will be 16 samples in an array. Really cool stuff here. So I'm adding this data loader, and now I will ask those of you who are alive so far, because again, we're not yet reached the most fun things here, but at least we're getting there. So I will ask you if you implemented so far. So I'm adding this to the Jamboard, Whiteboard. So the slide number 13, this is added. And my question to the group will be, is this ready? So data set and data loader, and then we'll jump into the fun things, the model itself. So is this ready? Plus minus. If minus, then maybe you could write in progress, maybe in progress or anything. So I know if I should wait or okay, somebody is done. So that's excellent. Thank you for responding. Let's wait for somebody else. In progress, minus, you give up. You cannot follow. You need to do it yourself slowly. Any answer, so I know if we should move on. Right now I have just one plus, but let's wait for somebody else. Again, reminder, if you do well with this, happy to take you in the thesis research, commercial research, academic research, all sorts of cutting edge research. So those of you who want to do this professionally, please bear with me. And those of you who just want to pass the course, then yeah, you also need to bear with some resilience, and maybe you don't need to understand every single aspect of it, but enough to at least to get to the exam, basically. So oh right. So I'm not yet get to the optimizer, but it's great that you're following up. So yeah, so if I go down to the next part, so this would be train test split. So it is split like this. So I'm saying that we will split from this particular index at particular position. Yeah, and it's not actually random. It's just the fixed position in my length. So it happens to have the last samples. Hopefully they are sort of randomly sorted. I'm not actually that sure, but hopefully. So that's that. Then variable. Oh, but we have not yet get to the SGD. SGD we will do as well. No worries. So then the variable. I think we don't need to change variable at this moment. We'll try to make very simple model first. So then the linear layer. Linear layer is the most complicated stuff. So you will need to bear with me a little bit. Let's try to make it, and then we can actually make a small dummy code to make sure it works. This small dummy code. Let me think how to do this better. Okay, I think I know. So if I have a linear layer, linear, right, I have an idea how to do this. So you can also do a small dummy code. So if I write here dummy x, this will be variable variable, how I define variables. Second. Right, I remember. So variable value, and this will be MP 0. Zeros means just the empty matrix, right? So there will be, let's say, 5 comma, right, this is dummy. So the dummy will be, so the batch size comma, let's say 5. So this is my dummy variable, and I will have dummy linear function, linear layer, and in features, of course, will be 5. Nothing else will work. Out features will be, let's say, 7. So these are definitely not optimal values, but just for the sake. So, and then dummy output. This will be also variable. So this will be dummy linear forward dummy x. So this is the whole checkup code and exit here. So this is how you call these things, okay? And now we need to build these things. So first variable up there, so this is the most difficult one. This is our matrix. There is not many matrices at this point in our models. When we will have many matrices, we will do them in PyTorch next time. So random, uniform, it can be normal as well. I don't mind. You can use whatever you want. It just know that uniform works better for these strange small models. So size, and here will be in features, out features, and this is what it does. It is like zeros, but just creates with random variables from -1 to 1, just a noise basically. So and the grad so there are different ways how to calculate grad. One would be to sum it up at the every stage, or by the samples at the end. So in this case, let's do the samples at the end. So in this case, then it means that batch size stays here, but this is kind of also good learning here, because what it actually tells you is that gradient is something that is not for staying. So everything where you see batch size, this means this is something that will go away very soon. So in this case, it also go away very soon. Oh, I just forgot that the zeros have this parameter shape. It doesn't work like I wrote it here. I think you need to have either 2 brackets or shape. In the bottom part here, I also added shape. So let me keep attention here. See, there is a shape here as well. Oh, and shape in the top part as well. Okay. So that's that. So this is so the actual part which you need to care is this in features, out features. This is our product of this is the final solution for this model. So okay, so then variable next. Again, if somebody is scared, is confused, what means this syntax? This syntax in other normal programming languages would be like this: variable. Python is very strange language. They don't have new. It could be that, let's say, in future Python versions, they think that to add new, they all the time add something new. So the new, but it's not there. So it's like a function called. That's why definitely please make all of your classes with large letters. If you will use them with small letters, you will confuse yourself. So value. And here, what we show, you know, the homework things. So basically, we will have shape, which is out features and not the extra dimensions. And for grad, and why actually I'm defining grad here, I could actually not define grad here, but I want to implement it the same way as in PyTorch with gradient accumulation. And you will see that in the SGD grad class, we have 0 grad function, and you will understand what it does after today. If you don't do this work, then you don't know what 0 grad does, basically, but it makes sense. So that's that. And then the X and output we will not define, because they will come from the outside world, and we will produce new variable output, basically. And these two guys are the ones which we will target and train. So we will find them, cherry pick from the model, and send it to the optimizer. That's our plan. And here I actually did some typing as well here. That's good. Yep, I will not try to scroll too far away, just sorry. So I will add the dummy code to the whiteboard, and then the top part, and we'll slowly get to the next part. And even though you might think there's like huge amount of code, it's actually not. The linear layer is the most complicated. All other layers are really just very simple. So the top part, and why actually the linear layer is complicated, only because there is these matrix multiplications. So others don't have matrix. So there is W times X, and W times X is self, not times but dot product. So W dot product value, and here there is a small trick. I need to transpose it. The transpose is really trick, because it really just depends on either you put in features, out features as a columns and rows. Maybe you don't need that. And also, even if you do, then in backward pass you would still need to have transpose. So X value, and then we do this trick which I explained you already. So we have these two dimensions copied, and we will add new dimension with my non, which I like. So like that. So it just adds another. So because if I have X before this moment, it is just batch comma features. Now it's batch comma features comma 1, and it means that my weight will be executed with these two last dimensions, and it will not touch the batch dimension. So that's that. Then I want to have the output. So the output is the same. It's just that I will drop the last dimension. So, and dropping the last dimension is as easy as selecting the last dimension. And finally, we need to produce the output variable. And this is wx plus self b value. Really simple stuff. So you see the forward pass, as always, very simple. Like almost every deep learning function, the forward pass is like really the leisure time, nothing difficult there. The backward pass is where the problems start. So that's that. And then go to backward pass, and backward pass, for your sake here, I will show. Again, it's not too difficult. Sometimes I ask students to do this themselves, but already taken quite a lot of time, and some of you already gone away, could not survive the mathematics, but okay, it's not that difficult. So output grad. So what we do here, this is this kind of cool. So we will start using the pointers of the outputs which we produce. So this is we stored the output, and then when we do backward, we still have this pointer here, and which is really fun. Maybe if you stop here and look at this a little bit. So the output I create here, right? But gradient is created in the next function, which I even don't have it here. So the gradient, this dot gradient, will be implemented and calculated in some other function. Like for example, if after a linear comes the sigmoid gradient will trickle down in here, and then I can use it in the chain rule. So that's really, really cool. This is like using the object-oriented pointers of objects to achieve the chain rule. So this is the derivation of linear layer with regards to b is 1 times this. So this is so what it is actually. So this is okay. Let me write the whole stuff. Plus b by db, right? db equals 1 times chain rule. And why chain rule? Because we have the onions. So what is the chain rule is that I have, let's say, tan h over linear over tan h, and every time where I have this bracket, I just calculate the upper derivative, multiply by the next one, multiply by the next one, multiply by the next one. That's how the chain rules work. And with the object-oriented programming, it takes it to the whole another level, because now I'm passing the variable to the next layer and then calculating gradient and then calculating it back. So this is backward propagation, really, really powerful. And by the way, if somebody didn't know, the last week, the Geoffrey Hinton, who invented this stuff in 1990, about like 1989, they got Nobel Prize. So I think in chemistry actually, because the neural networks, quote unquote, basically solved the AlphaFold. So the person who invented this stuff got Nobel Prize, and you're now implementing the stuff. So that's quite cool, I think. So self x value. So the gradient with regards to w, there's x. We already did this many times before. If it's not clear, you need to go to previous lectures. So this, non, again, I need to have another dimension. Then self, and then this becomes really, this is actually fun, but it's not self-evident. So we'll try to explain. So what I'm doing here, and this is definitely why you cannot do this just dot product. So is that you will need to have orthogonal vectors. So you notice I'm adding the none here and none here. What it actually means is that the first one will be, so if I'm not mistaken, vertical, another one will be horizontal, and then what? Yeah, it should be horizontal. No, wait. Yeah, it is horizontal, sorry. So horizontal, vertical, horizontal, and if I do dot product by vertical, horizontal, I will end up with matrix, which will be the size of the W shape. So, and you would not be able to do this if you don't put new dimensions. So that's something to keep in mind. So that's one. Yeah, and the output grad will be vector, and this will be also a vector. And just also please remember that matrix as a data will always be only the W. These other guys, everything that travels through the model, if it's not an image, if it's not a picture or something, they are not matrices. They are just vectors with repeated dimension of batch. Maybe it's not clear at this moment, but just keep trying to track this. So at the end it will be clear. So let's keep digging. So the next one will be the x grad, and here let's split it again in two operations. So self w, again this will be matrix stuff. Self output grad copy none. If something doesn't work, try to make a screenshot, share it somehow in the chat, and I can help. If yeah, and you can try to write an email, but I'm not always able to respond quickly. If you ask me multiple times, I will probably respond. So, but and also definitely come when I go to some like in on-premises locations, right? This is very hard for me to do, but sometimes, not sometimes, but when I'm in Latvia, I will go to different locations and do these classes in person. Then I can explain better. So copy 0. Okay, it seems about right. Seems about right. And then we need to run the dummy code. We'll see if it's right. Maybe it's not right. In these models, very easy to make mistakes. So okay, so if to run the model, I would add here breakpoint, run it debug, and please not crash. Okay, it did not crash. That's a good sign. And by the way, I added the code on the slide number 15, if you're wondering. So the dummy x, so we'll see if it works. So value, shape. So 16 by 5, that seems about right. And what is the output value? Value shape. It before I'm running, I can tell you it must be 16,7. Yes, it is. It works. If you get something else out there, it doesn't work. Or it probably will just crash somewhere and tell you have wrong dimensions somewhere. So this is that. I will also comment this part so we can move forward. Yeah, this is the whole code you need to cover so far. If any line is not clear, you can try to tell me which line, ask particular question, and then we'll move on to easy things now, because these were the hardest one. Then the next things will be easy. So, oh, we lost another guy. So we have we have only 7 survivors left today. Please try to survive. The results will be good, I think. So yeah. So is linear layer ready? Plus minus. If you have some problems working, you can write also maybe working on it. Working on it. Okay, great. One is ready. So let's wait for somebody else as well. You could, if it's ready, definitely try with the dummy code. If it fails on the dummy code, there might be some problems more. Okay, we have 2 ready. I think the funny thing is there were many English-speaking students, and only Latvian students seem to be tracking. Maybe it's some English-speaking as well, but good job, guys. If you are English-speaking and you're tracking with me here, then you can write in the chat, because it seems in the chat that only Latvians are getting along here. I had some couple of international students who were able to succeed with these courses. Not couple, but many, but some that are succeed in the way that they led their master thesis, basically, or bachelor thesis and so on. Usually when I do some bachelor and master thesis, we also publish some scientific work. So that's what we do. Okay, we have 2 pluses, nothing else. Nobody is saying that they cannot do this. Please don't be ashamed if something. Okay, so I think I should move on, because already we'll be running over time, but hopefully not too much. I will try to not run too long after the time. There will be one aspect which I probably will leave out for today, but I will kind of, let's see, do we have it here? Yeah, layer embedding. I will discuss and show you what it is, and then probably next time we will implement properly. And those people who want to be great at this thing and really want to, do road level stuff, which even this is not really like anything crazy, it's difficult, it's quite easy. They should implement layer embeddings themselves at home, maybe. We'll see. So, but this is not difficult, really, promise you. So the sigmoid, this is now the fun part, because these will be easy. So output x stays, should this stays? Yeah, it stays the same. and then the output is easy, as I say. So this will be a variable, and let's do the spaghetti here, small spaghetti. This will be short macaroni. And exponent, where are you? This is, hopefully I did it right. I need to look for the equation. Oh, there should be minus sign. Okay, minus x value. And the gradient is also very, very simple. Now, we even don't need matrix operations here because this will be element-wise operation. The gradient operation starts to be issue when you have at symbol in the forward loop, forward pass. If you don't have it, then it's no issue. Grad, yeah. So this is the x input times self out. All right, and the output actually. So this is a little hack because basically this is the sigmoid value basically. So and oh, there should be wait, I made a mistake. So there's a value. Here's also value, and then the grad at the end. So this is a small hack just because I don't want to repeat the same equation here. Really simple. I don't think you cannot like mess up this one. So okay, so I'm adding this to the whiteboard. We'll move to the next stage. This is added. Oh, relu, please implement relu at home. This will be also fun. So what else we need? Mean square, or which one do we want? Mean absolute error maybe. Okay, cool. Let's do mean absolute error. So was it required mean absolute error? Yeah, it is required. Okay, cool. I already gave the derivatives as well. So again, this will be super easy. So MP, again, it's always better to use mean value rather than sum value, because then it's dependent on the batch size. If you have large batch size, you will have large sum. So that's as simple as it gets. So Y value, remember to use value, because we could actually implement the override of the minus sign. This will be actually quite fun, but let's not waste time on that. So, and PyTorch and Numpy actually do this. They override minus signs so that they don't need to use value. So that's that. Okay, and then the gradient. Okay, we can also use some temporary variable here. So self y value. Again, very important order. If your order will be off, everything will not work. So the order, I mean the order of variables in equation. Because on the forward pass, you don't care about that. On backward pass, it's critical. So then, and again, please notice the gradients here are always accumulated. They are not just equal. That is by design. So NP absolute value of temporary, and then we could do smoothing, we could do other type of stabilization. So like that. I believe that's good. That should be good to go. Slide number 17. And now we get to, the model. I was thinking I would get to optimizer. So the model, but model is actually also quite fun, easy stuff. So how you build the model? You do the layer linear, and you have the in features. In features, this case you have 6, but I remember I told that first 4 should be separated and used with the layer embeddings, but we'll get there. So out features will be, we can define as much as we want. So let's project in high dimensionality. So to visualize this would be like you have shadow on the paper, and then from that shadow you're trying to reconstruct 3D object basically. It's kind of like that. So layer sigmoid, and then we will project it down, I guess. Let's try to project it down to 50 dimensions, and then project it even more down to 2 dimensions, because the data which we are feeding in as the true results, the ground truth, it's called ground truth in deep learning, you have 2 dimensions, the owners and the price. So the inputs 6, the mileage, I mean, like, you know, kilometers, year, whatever, a brand. Even though brand, please never do this, what I do now here, brand cannot be inputted like that. This is totally wrong. So, and outputs are 2-dimensional, and this is like owners and price. Good. So this is our basic model, and here you can have your creativity, do all sorts of interesting models. About model architectures we will talk later. There are ways how to do this correctly. So, and then forward pass is also very simple. For layer in self layers, and just pass it through down the layers out. So layer forward, I know in you'll see. So yeah, out, yeah, really simple. And for the backward pass it's even more simple and even more fun. So for layer, because you will see there is a nice function. So reversed, Python has this nice function reverse self layers, and then you can just go from the other side and do the back propagation, and back propagation goes literally as simple as that. So you will first calculate all of the output pointers, and then you use those output pointers to connect your layers for the backward propagation. That's great. And parameters, this is also the same way as in the PyTorch. We need to fish out those parameters which are learnable. Remember I told that sometimes you could even learn the inputs, which in this case would be like some kind of style transfer or something. But in this case, we definitely don't want to change inputs. So self layers, and let's fish out linear layers. If is instance layer equals linear layer. Yet if this is a linear layer, then we will fish it out. And how we will do this? Variables plus like that. This is like a short small trick of Python to have multiple variables appended to the list. That's literally it. So this is, I think all of the mathematical part for the model is covered already. Now we need to just make it work. So this is the model, and I will wait for you to catch up with the model. At least somebody hopefully will get survivors to the end, because we are close to the end. So this is 18 slide. Yep. So is the model ready? And let's answer plus. Minus means, oh shit, I think something froze. Okay, plus minus, and W means working on it. Okay, so please type in the chat, and then we will move on to the next stage. Meanwhile, I will look what's up with my hotspot internet. Yeah, this is so crazy. I'm doing this lecture from Dubai using the hotspot internet because there's bad internet here in the hotel. So plus 2 plus is great. At least 2 people are tracking. and they are not English speaking. Okay, so the next optimizer, SGD. So this is again one of those simple things. As remember, I told that we were keeping the batch dimension in our gradient operations, which is one way to do this. We could also have the mean values after, but no, I think that would be correct way to keep it in there. So at the end we need to have this either summation or the mean value, and mean value we could add it here. So I know this is not exactly the same equation as in the mean so what I'm saying here in the absolute error, we have mean here, but I don't have it mean here. At the same time, so let me think, where is the grad? I could add it also there actually. It should work also there. Yeah, but yeah, that's fun question. Yeah, I think it would be more correct if we added. No, it would not be more correct. Okay, let's leave it here. So if I will start explaining that, then we will never end. But okay, the mean value will stay here for sure. So param grad. But it is basically what it is. It is that I'm calculating the mean gradient from the batch at the mid stage of my model. There are some advantages of doing that. So dot axis and self learning rate. The axis thing is important. So this means I'm liquidating, I'm removing the batch dimension and leaving the feature dimensions. And then if the feature dimensions are the right shape as this thing, it works. So if I have a matrix, this should also be a matrix after this operation. If there is a batch, then it doesn't work. So, and then the zero grad, you see here, it's just like zeroing gradient accumulation. And again, why do we have it here? It is because I'm just trying to show you how PyTorch works, and PyTorch also have this, so that if you have two large batches or two large samples, you want to have ability to create virtual batches, or also this is extensively used in recurrent neural networks and other models. So this is something to keep in mind, that you cannot just keep calling backward forever. You need to zero grads when you need to do that. You'll see that in a second. This is the optimizer. Really added just one line there, nothing difficult. And we'll see if our monster Frankenstein works at the end. So I don't know, hopefully. So layer embedding, super important stuff. We'll cover it a little bit later. Probably not today, just will explain what it is, but basically it just will take too much time right now, but it is important. So then epoch training, and let's implement the training stuff. Training stuff should not be that difficult to implement. So how we do this, we literally call the model forward, and then we create a new variable. Everything that we pass to the model is variable, because we need to have the pointer to the gradient, pointer to the previous layer and gradient. And this is actually tensor. I could just maybe I should rename this in my templates as a tensor. Variable rename tensor, and also value to data. So in PyTorch, the value is called data, and grad is the same as it is here. So, and then the next thing is loss. Loss will be so the loss will be also calculated with the forward pass. So forward, loss function. Okay, here. And here we'll also have variable. We always have variables or tensors, in other words. And here will be y prime, which already is variable because it's returned from there. And then the fun thing here, very, very important. We only train model when we are in the training phase. If we are in the test phase, we never train model. We don't touch weights in the test phase. So what I mean by touch weights, this is also very, very straightforward. So we say loss function backward, and then the model backward, and then the optimizer step, which is the optimizing step, and then the zero grad out just after that. What I just wrote, it's almost identical in PyTorch, but now you know what it does basically. So that's that, and then if we are lucky, this should somehow work, we'll see. And then I need to explain a little bit about layer embeddings, and then we will wrap it up for today. We'll have also kind of small fun homework. And next time will be super exciting because we'll start with the PyTorch. Also, there is possibility that next time I will be in Riga. Might be. Yeah, I think it's like most likely. I will double check my calendar in a second. On Wednesday, Riga probably. Probably I will be flying back already. Hopefully I will get some sleep. So that's that. Okay, let me run this code. So run it. Oh no. Okay. I did it myself. So list. Let's see. So this should be small letters maybe. Okay, works. Oh, nice. It works really nice. So maybe we will get also the overfitting. So what is overfitting? But it's actually hard to overfit such a simple sample. But I will show you. So it works actually. You need to get to this point, and then I will explain. I will now explain a couple of things, and basically you will get to this point. So it works. So let's jump back to the whiteboard. So all of the code is in the previous slides. Explanations is in the video. So, but then there's a couple of important stuff. So then one fundamental stuff to understand is that there is such a thing as overfitting, underfitting, and yeah. So the main thing which you want to avoid is called overfitting, and the overfitting looks something along these lines. So you have epochs and these training curves, the test loss and the train loss. And what you'd want to do is actually usually to choose really large model, like that here, like 10,000 hidden states and so on, to have the situation that the red line starts go. Yeah. So actually there is in this case, this is a blue line. The test line goes up, so the validation, and actually also the terms are so messy. I like to say this is a test line. I think the YOLO people say this is a validation line. There's it is not 100% term actually. So, but there are at least two sets of data, sometimes three, sometimes even more. So the validation, when it starts going up, what happens here is that the model is learning every sample by heart. Basically, it is not learning any kind of logic between samples. It is starting to get very good at recognizing the samples themselves. So what you want to do is actually train model to this point. You want to have large model overtrained. That is what you want. But you want to save model at this moment where the test loss is the lowest. This is the right place to save weights. And when you say weights, this is your final solution, the product. So this is the thing you will deploy on the let's say Bitcoin price prediction or whatever. So you will deploy this guy here. So this is the over, and if you are actually on here, this means you're overfitting. Fitting. If you have underfitting or any other strange situations, that probably means you have bug. Basically, there's no normal ways these other things happen. It's just like bug, most likely. So and if you have this situation where it fits normally and it's basically not overfitting, that also is not a great sign. It usually means that either you have too simple task, or you're not using enough large model, or any other hyperparameters are not optimal. Okay, so let me talk about the one last thing before I wrap up. So what is that linear layer? So linear layer, actually, I mean the embedding layer. Embedding layer is basically the linear layer. That is very, very simple. So, but at the same time, it is something a little bit more than that. Okay, let's go from one side. So we will talk about this next time again, but you need to start thinking about it. So let's tackle feature. So the feature will be, so if I take sample 0, yeah, then and then the first the dimension, this will be sample 0 brand, right? And in this case, the brand could be BMW, for example. Okay. Hopefully you follow up. So, and then for the next sample, this will be brand Audi, right? And then for the next sample, it could be something else. I'm here in Dubai and I'm renting out Suzuki. I even didn't, I also rented out some from the Yak. I didn't know such a car exists. I think it wrote like that, or Suzuki, whatever. I even don't know if I write it correctly. Probably not right. Suzuki. So, and these guys, so they are not, of course, any kind of tokens. They are actually indexes. So this will be index, let's say 2, index 4, index 7, whatever. There are more brands than these, right? So that's that. But this is a very bad way to input data. Because what it actually means, let's even have here 8. So what it means is that you are saying model that Audi is 2 times worse than Suzuki, because it's 2 times less value, and BMW is 4 times worse than Suzuki. So Suzuki is a very cool car. It is so much times better than any other car. It doesn't make sense at all. So, and if you change the order, everything becomes even worse. So definitely not a good way how to represent data. You should never ever feed any model something like that. If you do that, it automatically shows that you don't understand what you're doing and probably not get a good job in these kind of fields. So the other option is one hot encoded. So this would be much better. Okay, we'll not write the whole stuff, but basically if I have 2, it means there will be something along lines like this. So maybe let's write the full stuff. So each car will have unique vector encoding. So how I go? Okay, so now I have it. So this is a whole vector for BMW, whole vector for Audi. And you might think this is not a big deal, but it is. So, because the distance between these vectors will always be same. So it will always be 2. So basically the distance between these 2 guys and these 2 guys is not the same. The distance between any of these are always the same. So this means that this representation is like way better. So it doesn't mean, so it doesn't matter in which order you put the cars, it will always have some meaningful representation rather than saying that Suzuki is 4 times better than BMW. So you'd never do that. Okay, so that's one. We have 6 survivors yet. Okay, so great job, guys. Those who survived so far. We started, I think, 12, so half of you already gave up. Hopefully next time we'll have better results. So, and then what is the embeddings? So embeddings, which, by the way, embeddings and vector databases, is super cool stuff. Especially for the word embeddings, for text embeddings, image embeddings, well, data embeddings, really powerful stuff. So this is even cooler than one-hot encoded because I can have arbitrary dimensions. I can have W, let's say W1. So this will be for the BMW, W1, W2. For the Audi, it will be W3, W4. What you see is already, even though I have, let's say, 8 car brands, I already, there's 4, 5, 6. So even I have 8 car brands, I have 2-dimensional representation. That's powerful. Also, the representation initially is initialized as zeros and then slowly learns itself. Rather than this on the top part, the one-hot encoded is hard-coded. This one is not hard-coded. This learns themselves. And how it learns themselves is something along lines that you have 2-dimensional embedding space. So this is not some kind of real space. This is embedding dimension 0, and the other one is embedding dimension 1. And the really cool stuff is this. So you will start by training these models. Let's color code them. So this will be red, will be BMW. We will start it here. You can start also from random positions, but let's try to make them, they're all the same. So Audi is here and Suzuki is here. So one thing is good, that all of them are kind of the same. At the same time, which is not good, that all of them are 0, so not cool. But when you train them, what will happen is that Suzuki will go here and BMW and Audi will go here naturally on itself without your human interaction, which is super powerful. So after the training and before the training, so this will go after the training to these locations. And why? Because BMW and Audi are like German cars. They are more similar to each other, and Suzuki is different. And the same thing will happen with every single data types. So this is, you see already how powerful it is. So, and how to do this? It's actually really simple. So either you have like a this kind of matrix where you select physically out this this vector, which is variable learnable, or you can even have something like embedding equals the embedding matrix or at the, let's say, one hot encoded vector. So this, the same effect will happen. Either that or physically select the weights out of it. So that's that. What I could do, the layer embedding is actually implemented very well already. I gave you the implementation there, and it's actually random, not zeros in the beginning. How to use it? Let me see. I don't want to take much of your time anymore. So basically, I will maybe add some small example for homework, but think about it, start implementing it. This is very powerful. You already learned a couple of very important techniques today. And the idea is next week, let's meet, let me check the calendar, just a second. I don't want to promise something they cannot deliver. Whoa, what is the UK seminar? A little bit scared about that. Some kind of seminar is scheduled sometime. Okay, so anyways, let's try to meet next week. Oh, I don't like that it's 5 o'clock. That's strange. So I think the best would be for anyone after the work, right? Not in the middle of the working day. So I would say like 6 o'clock RTU on Wednesday night in Riga. That would be kind of optimal time for me, and then I can meet you in person. Those of you who are not met in Riga, I will also come to Liepāja and Ventspils time to time. So please schedule yourself for the next week. Not last time there were very few people on person. That is not optimal. Please come. Okay, so that's it for today. Let's keep in touch. Bye bye.